Welcome back, beautiful people of BC Calculus. Are you ready to talk about non-comparison tests? In the last video, we talked about the two tests that we can use that are comparison tests, right? We talked about direct comparison, where you have to have another series to compare it to, and then you kind of convince us using words that it also converges or also diverges. And we talked about limit comparison, where again, it's a little more technical version of the direct comparison, where instead of convincing us with words, you put it in a limit, right? The problem with both of these, well, in my opinion, there's two problems with these. One, you have to come up with a series to compare it to. And two, you have to know the behavior of the series that you brought up, right? So you can't just say, oh, okay, well, I have a nice series that I think is close to this. If you don't know what that series does, if you don't know if that series converges or diverges, it's no good to you. So not only do you have to come up with a series, but you have to know the behavior of that series. So for me, those are kind of like deal breakers, if you will. I'm not using either one of those tests unless I have to. Okay, so the two tests we're going to talk about today are no need for comparison tests. In other words, you do not have to come up with another series to compare it to, and that is fabulous. We just take the series they gave us and work with that. So I always go for these first. If they don't work, then I go back and try to work with integral or direct comparison. Okay? All right, so the first test that we are going to do today is called the integral test. I know, right? Just when you thought series couldn't get any better, we bring in integrals. You're welcome. Okay. Now, the integral test may not be as bad as you think, though. We'd only use it really for very simple series. And the idea is this. If you have a series and it has an infinite number of terms, they say, you know what? Let's think of that series as a function instead. Okay? Whatever this series rule is, I'm going to rewrite it in terms of x instead of n and just treat it like it's a function, right? So let's say this is my series when it's in function form. Right? These series have finite terms that get added up, and we need to know if those are adding to infinity or not. Well, guess what? Another way to add an infinite number of things up is an integral. So basically, the concept here is that every term in this series is like a rectangle that would have been under the integral, or an area under the curve, right? And since notice I'm making my integral go out to infinity, I have an infinite number of rectangles. And each one of these rectangles is representing one term of the series. The integral adds them all up, and we find out, does it go to infinity or not? Now, obviously, this is an improper integral, so this brings back all that limiting process and all that good stuff. Is it fun? Not necessarily, but you don't have to explain yourself, and you don't have to come up with another series to compare it to, which is key. So, if I can take my series, if it's simple enough that I can look at it in terms of x and just integrate it, I can answer the convergence divergence question pretty quickly. If it's a more complicated series, if it has a factorial in it, I'm not going to be able to integrate that. So the integral test isn't going to help me. Okay. But if it's a simple enough series, the integral test will work very quickly. Okay. So I'm bringing this one back. We already proved this by direct comparison. When we talked about direct comparison, we said, okay, well, the series 1 over n, that diverges. That's the harmonic series. And this is 3 times that. So if 1 over n diverges, obviously, if you multiply all the terms by 3, it's going to diverge. Infinity times 3 is infinity. But we had to write it out, right? We had to create an argument. We can prove that same thing using the integral test without having to write out words. And really, it's just a matter of what you prefer to do. I don't like to write things out. I feel like I always talk myself out of a right answer. Okay, so if we want to use the integral test for this, here's what we're going to do. We're going to take this summation and rewrite it as an integral. So instead of sum from 1 to infinity, I'm going to write the integral from 1 to infinity. And then I'm going to rewrite this function just in terms of x. In other words, I'm going to replace all the n's with x's. You don't really have to replace the x's. I suppose you could just integrate in terms of n. There's no harm in that. People tend to like x's, though, when they're doing integrals. The idea here, if I integrate this, if this comes out to infinity, my series diverges. If this comes out to something finite, my series converges. In other words, the series is going to have the same exact behavior as the integral. So in chapter 8, we talked about integrals either converging if they come out to a finite number or diverging if they come out to infinity. All I have to do is evaluate this integral, and I'll know the answer to what's happening with my series. Now, this is a simple enough integral to evaluate. So the first thing that I have to do is get rid of that infinity, right? This is an improper integral. You have to treat it as such. So we have to write this out. Taking that infinity out and instead approaching it. So if I integrate this, the integral of 3 over x is just 3 ln of x, right? So I get 3 ln of a minus 3 ln of 1 if I integrate that. Ln of 1 is 0. So I'm left with the limit as a approaches infinity of 3 ln of a. As a approaches infinity, this goes to infinity, and I say it diverges. So if I can show that the integral diverges, I've shown that the series converges. Convenient if it's a simple integral. Not so convenient if it's a non-simple integral. Impossible if there's a factorial. As soon as you see a factorial, integral test is out. I don't know the integral of x factorial. Okay. So, on your flowchart, let's add the integral test under no need for comparison tests. Don't need a comparison. Okay. Also, let's just go ahead and add now, under no need for comparison tests, the ratio test. Now you may notice that the ratio test got a fancier, much larger font. There's a reason for that. It is hands down the best test that has ever existed. Okay? This is literally where I go if geometric p-series and nth term fails me. Ratio test is the first place I go. The only way I use any other test, there's 2 reasons I would use another test. The ratio test failed me, or they specifically told me to use another test. Otherwise, I go through those first 3. Is it geometric? Is it a p-series? Does it fail the nth term test? If none of those grab it real quick, I'm going to the ratio test. Love the ratio test for so many reasons. Number 1, it's a no need for comparison test. I don't have to come up with another test. Number 2, I don't have to explain myself. It's all just evaluating a limit. And number 3, it's easy to interpret. So remember with the limit comparison test, it was like, well, if this, and this has to converge, and this has to diverge. No such thing with the ratio test. The ratio test is much more straightforward as far as interpreting it. And as if all of that wasn't enough, if it wasn't the best test already, sometimes, and you'll see very soon in the next video, we can get extra information out of the ratio test that we can't get out of any other test. It's the best one. Ratio test all day. Okay, ready? Let's talk ratio test. Okay, best test ever. All right, here's what the ratio test does. This might look crazier than it is. The ratio test compares 2 terms of the same series, and it does it just kind of in the general form. So a sub n is the nth term of a series. A sub n plus 1 is the next one, right? So it's comparing the 10th and 11th term, the 11th and the 12th term, right? The 100th term and the 101st term. And notice what it does. It puts them in a ratio. Okay. So think about what we need to be happening for a series to converge. Right? I need my terms to be getting smaller, the minimum, right? So if my terms are getting smaller, think about what this ratio is going to look like. Okay? I'm going to take this out to infinity, right? Do my limit. And here's what the ratio test tells us. One of 3 possibilities. Okay. If the thing that comes out of this limit is less than 1, we know that the series converges. Okay, now think about what that means. If this is less than 1, that means this term up here was smaller than this term down here. If this limit comes out greater than 1, the series diverges. About what that means. If this ratio comes out to greater than 1, that means the term on the top is bigger. That means your terms are getting bigger. That can't be converging. Okay? The only way the ratio test fails us is if it comes out to exactly 1. If it comes out to exactly 1, it's inconclusive. Right? In other words, it's too close to call. You get any number, and this is absolute value, right? Because I don't know if you can see under my floating head here, it says no negative terms. Because we're in the big rectangle, you cannot have any negative terms, right? So if, as long as that ratio comes out less than 1, so in other words, since it's absolute value between -1 and 1, we're good to go. It converges. If that ratio comes out any bigger than 1, I'm in trouble. If it comes out to exact 1, I'm also in trouble because I have to go use another test, right? But this is hands down the best test. All right, so the only part of the ratio test that sometimes people find tricky is simplifying it, because you're going to have a fraction and a fraction, but we'll talk about some strategies for getting these simplified in a pretty straightforward way. So let's take a look at one here. So let's check the series for convergence. So let's just go through our list just to make sure. Is it a geometric? Not a chance. I got excited. There was a 3 to the n down here, but then this n squared plus 3 ruined everything. Okay. Is it a p-series? No. Right? To be a p-series, I would need n to the power down here, and there certainly wouldn't be an n up top. How about nth term test? Does it fail the nth term test? Well, let's see. Let's write out a couple terms. I need my terms to be approaching 0, right? When I put in a 1, I get 4/3. When I put in a 2, I get 7/9. When I put in a 3, I get 12/27. Okay. It sure looks like these terms are getting smaller and smaller and smaller, right? It sure looks like these terms are approaching 0. So nth term test isn't going to help me. If these terms were getting bigger, I'd be like, nth term test fails, 5 diverges. Since my 3 easy ones failed me, I'm going into my big rectangle, and I'm using the ratio test. It's going to be my first one every time. So what the ratio test tells us to do is it tells us to take the limit as n approaches infinity of the n plus 1th term over the nth term. So the n plus 1th term is literally just this rule, all the n's replaced with n plus 1, right? So I need n plus 1 squared plus 3 over 3 to the n plus 1. That's my n plus 1th term. And then that has to be all over the nth term, which is just this. It was given to us, right? N squared plus 3 over 3 to the n. No, that looks like a lot. I get it, right? By the way, technically, again, because we're not allowed to have any negative terms in the rectangle, there are technically absolute values around this. I never write them. They are just so distracting to me. I don't write them. You don't have to write them. AP is going to forgive you if you don't write them. If I was writing it on the AP, I would probably go back at the end and put absolute values around everything. But I find it really annoying to carry them along with me. Okay, so look. You have a fraction. I know this looks heinous, right? But look. All I'm going to do is I'm going to do an invert and multiply. So I'm still going to have my n plus 1 squared plus 3 over 3 to the n plus 1. But now I'm going to bring this nth term up and just invert and multiply. So it'll be 3 to the n over n squared plus 3. Sometimes I don't even write this part. I just immediately do the invert and multiply. Right? I don't even need to look at this. This is hurtful, the way this looks. Once you have it written like this, it's going to simplify like crazy. Like crazy. Now remember, I'm approaching infinity. So things like plus 1 don't matter. Things like plus 3 don't matter. So what I like to do is I like to take my terms and kind of regroup them, right? And here's what I mean by that. See how this term has an n plus 1 squared plus 3, and this has an n squared plus 3? I'm going to rewrite those in one fraction. And then this one has a 3 to the n, and this one has a 3 to the n plus 1. I'm going to write those in one fraction. It makes it easier to simplify. Okay, so look, as you approach infinity, these plus 3's don't matter at all. And as you approach infinity, that plus 1 doesn't matter at all. So what you end up with is n squared over n squared. This is approaching 1. Okay. If you don't feel comfortable with that, remember the trick that we have, that as long as you have polynomial over polynomial, all you have to look at is the first order terms. So if you FOILed this out, this would have be n squared plus blah, 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 n squared down here. I can throw all the lower order terms away. It's just n squared over n squared, which is 1. So this whole first chunk goes to 1. Over here, it's a freakishly easy simplification. Let me erase over here. There's a couple different ways to think about this when you're simplifying 3 to the n over 3 to the n plus 1. Okay, look. If you have 3 to the n over 3 to the n plus 1, the way I think about it is this. I don't know how many 3's you have up here, but I have one more in the denominator. I have an extra one. This simplifies to 1/3. You could think about it in technical terms. If you break this up, this is 3 to the n times 3 to the first, right? Rules of exponents. The 3 to the n's cancel, you end up with 1/3. So this madness, this craziness here, really simplifies down to 1/3. Okay? It's just a matter of where your extra n is. So think about it with numbers if you want to. If this was a 3 to the 6th, this would be a 3 to the 7th. If this was a 3 to the 100, this would be a 3 to the 101. I don't care what n is, there's always going to be one more 3 in the denominator. So this simplifies down to 1/3. So this is 1/3. So the limit as n approaches infinity is 1 times 1/3, or 1/3. That's less than 1, I have convergence. Period. It converges. I didn't have to come up with another series. I didn't have to write any sentences. I just had to do one little limit. Okay. And I have an answer. Okay. And I don't even have to do like interpreting. It's less than 1. Done. Okay. Let's do another one. Okay. Does this series converge or diverge? 1 over 2 to the n minus 1. Let me tell you something. One of the things that I like to do before I do a series, before I do convergence, is kind of decide what I think is going to happen, right? It helps me. I'm going to ignore the minus 1 because who cares about a minus 1, right? 1 over 2 to the n, that's probably going to converge, right? These terms are going to get really small pretty fast. This is going to be, if you were looking at 1 over 2 to the n, it would be like 1 over 2 plus 1 over 4 plus 1 over 8. They're going to get small real fast. So I'm guessing we've got convergence coming, but it's nice to predict. All right, so let's do the ratio test. The limit as n approaches infinity. I need my n plus 1th term over my nth term. So my n plus 1th term is 2 to the n plus 1 minus 1. And then I need to divide by my nth term. So I'm going to multiply by 1 over so that I can save myself some writing. So this is divided by nth term. All right. If I can evaluate this limit, I've got an answer as to whether it converges or diverges. So, like I said, I like to do a little regrouping. 1 over 1, I'm going to write. Whoops, I forgot to write limit. Okay, so I have 2 to the n minus 1 on top. I have 2 to the n plus 1 minus 1 on the bottom. Recognize these simplifications. They happen the same way every time, right? I'm approaching infinity. I don't care about these minus 1's at all. That leaves me with 2 to the n over 2 to the n plus 1. In other words, however many n's you have up top, you have one more down here. So this simplifies to 1/2. it's less than 1, it converges. Period. Okay. Do you want to do one more just for fun? I kind of do. Okay. Let's do another one just for fun. Okay. Once again, it's not a p-series, it's not a geometric. The terms are going to get, let's see, this would be 3 to the first, and then 3 halves to the second, and then 1 to the third, and then 3 fourths to the fourth. As soon as you pass the fourth term, they're going to start getting small. The first couple are kind of weird, right? But by the time you go to the fifth, it's 3/5 to the fifth, and then 3/6 to the sixth, 3/7 to the seventh. So this fraction in here is getting smaller and smaller and smaller, and it's being raised to a larger and larger power. So these terms are going to shrink real fast. I'm guessing convergence. Yes. Okay. Oops. Sorry. All right, let's set it up. Oh, by the way, on an open-ended, I think I said this the other day, you also always have to state what test you're using, right? You have to say, by the ratio test, this is what I'm going to do. Okay, so the limit as n approaches infinity, n plus 1th term. So, negative 3 over n plus 1. Oh, wait, do you see what I just did? Mortal sin. I just tried to take a negative into the big rectangle. Tisk, tisk, tisk. You got to throw the negative away, right? So if you want to, you can rewrite this series like this. Right? You're allowed to break that up into 2 powers. In order to go to the big rectangle, I have to throw this away. Bye. Right? All you are is plus, minus, plus, minus, plus, minus, plus, minus, and I'm not allowed to take any negatives in. So I'm only taking 3 over n to the n. If this converges, then I'll know this guy converges too. Absolute convergence. Now let's go. Oh my gosh, I almost got kicked out of the big rectangle. Whew, that was a close one. Okay, n plus 1th term. 3 over n plus 1 to the n plus 1. There it is. That's the n plus 1th term. And then I need to multiply by the nth term, or divide by the nth term, right? So I'm going to multiply by 1 over. Now let's think about how are we going to do 1 over the n. What's that going to look like? I wrote n. Let's think about what that's going to look like, I think. Okay, look, it may be easier here to rewrite these with the exponent on both pieces. So, in other words, because then it's going to be easier to invert, right? Let me show you what I mean by that. I need to get myself a little bit more space. So if I write it originally like I'm supposed to have, right? Like this. You can rewrite these by distributing this power down to both, since this is just division, right? So this down here is going to be 3 to the n over n to the n. And then up here is 3 to the n plus 1 over n plus 1 to the n plus 1. Okay. Now, again, it seems like you're like unsimplifying, but I think that if you write it like this, it makes it more clear what you need to do, right? When you do your invert and multiply, there's a limit in here, you're going to have 3 to the n plus 1 over n plus 1 to the n plus 1, and then I'm going to bring this up, n to the n over 3 to the n, because now it's just a quick invert. Right? Now notice what happened. This just got flipped over, right? In other words, this became 3 to the n to the negative n. When we brought it upstairs, the negative just flips it over. So theoretically, you might understand that, but it's a little bit hard to see, so it might help you to rewrite it separated like that. Okay, so once we have that done, let's take a look at this limit. Okay, I'm going to rewrite it again. I'm going to do a little rearranging, right? I have a 3 to the n plus 1 and a 3 to the n that I can put together. And I have an n to the n and an n plus 1 to the n plus 1 that I can put together. This guy and this guy. Okay. Let's do some simplifying. As we approach infinity, nobody cares about plus 1s. This whole chunk goes to 1. Over here, I have one more 3 on top than I do on the bottom. Again, this is a 3 to the n times 3 to the 1, and this is a 3 to the n. Cancel. So out of this limit, I get a 3. So here's the thing. Ratio test says that's bigger than 1. So the ratio test says that diverges. Okay. Unfortunately for us, that's not the end of the story. As you may remember, we said when you go into the big rectangle, you're testing for absolute convergence. This series doesn't converge absolutely. In other words, when you take away its negatives, this series does not converge absolutely. Its absolute value will not converge. That's what we tested. Remember, we didn't test this series. We tested its absolute value. So here's the thing. If the absolute value diverges, we still have to consider that if the negatives were there, would it have converged? Right? If it was allowed to oscillate, if it was allowed to subtract every other term, would it be okay? In the same way that 1 over n is. Right? 1 over n diverges, but if you allow it to flip back and forth signs, if you allow it to subtract every other term, then it becomes the alternating harmonic series and it can converge. Right? So the fact that the absolute value of the series diverges tells us it doesn't converge absolutely, but we still have to look at what would happen if the negatives were allowed to stay. Now, you may be saying right now, but Miss Britton, we're not allowed to bring any negatives into the rectangle, and you're right. So we have one more test, and it's the only one that allows us to have negative terms. So if I need to put my negatives back in, that's where we're going to go next. But that's for another video. Okay, right now, take a moment, enjoy the ratio test for what it is. A beautiful, kind test. It's the best one. In the next video, we'll talk about what to do with this guy. What we can't say is, oh, diverges, we're done. No, the absolute value diverges. Now we have to go look at what the actual series itself does. Okay. Any questions that you have, pop them at the end of the video, and we will see you soon.